Here's Meghan Halse. Let's go.
All right, thank you very much. And I'd just like to echo the other speakers in saying that it's a great pleasure to have been invited to take part in this event, and that it's a very interesting and unique event, and hopefully will be something that we can continue on into the future. So what I want to talk to you a bit about today, some work we've been doing at York over the last few years on using SABRE to enhance benchtop NMR spectroscopy to do some reaction monitoring. So as we are all very aware, in NMR spectroscopy, there has been a move over many decades to develop NMR spectrometers with higher and higher magnetic fields using superconducting magnets. And so this has the great benefit of increasing our sensitivity and resolution, and now we can see 1.2 gigahertz magnets being installed around the world at the moment. However, there are some drawbacks to using such large and expensive instruments, which is of course that they're not very portable, and for some applications not very affordable. So consider you want to monitor a reaction and you want your instrument to be in a fume cupboard, then that's not going to work with standard NMR. And if you don't have many hundreds of thousands of pounds, maybe you can't afford an NMR spectrometer. So as well as being development of high field NMR, there's also been a rich development around the area of low field, benchtop, and ultra low field NMR. And so in particular, in sort of the last 10 years or so, we've seen a lot of commercial systems become available in the sort of 1 to 2 Tesla range, benchtop range, that crucially have chemical shift resolution. And these are usually based on solid state magnets, arrays of solid state magnets. So if we compare what you would expect to get in a standard NMR sample in a 5 mil NMR tube on a standard 400 megahertz spectrometer versus 1 Tesla or 43 megahertz, we can immediately see the challenges that we face. We have a reduction in our signal to noise ratio, and also because we've compressed the chemical shift axis, we also have significant peak overlap, particularly in proton spectra. Now you can also go to the extreme of going down to the sort of 0 and ultra low field area. Here I'm exemplifying this with Earth field NMR, where you lose your chemical shift information entirely, and you get a single peak for a single resonance, generally speaking, in the absence of heteronuclear couplings, and you need quite large samples. So for example, this is just a spectrum of 500 milliliters of water. So if we have systems where we are struggling for sensitivity, then obviously we're a community who would like to answer that problem by using hyperpolarization. And I'm particularly interested in using parahydrogen hyperpolarization because if you are using these low field instruments in order to have portability and affordability, then you can't then couple them to a hyperpolarization method that's way more expensive and non-portable. So as we've seen all through the talks today, parahydrogen is very attractive as a method for doing hyperpolarization because we can generate it relatively cheaply and easily, either using conversion at liquid nitrogen temperatures for about 50% enrichment, or at lower temperatures to get closer to 100% enrichment. And then of course we can store parahydrogen, so you can generate it in one place and then move it to where you want to use it. It's NMR silent until you unlock the potential for hyperpolarization using a chemical reaction. So as we've seen, there's 2 sort of general classes of chemical reaction we can use to unlock the hyperpolarization potential of parahydrogen. And I'm going to focus here on the SABRE approach, so signal amplification by reversible exchange. And we've seen some overviews of that this morning by my colleague Simon Duckett, who proposed this method first back in 2009. So I just want to give you a brief reminder about how we carry out this SABRE experiment, because it's quite relevant to the work that I'm going to talk about. So just in a sort of cartoon way, if we think about running a SABRE experiment, well, at its heart, it's a catalytic process of transferring the spin order or the potential for hyperpolarization from our parahydrogen to a target analyte or a substrate. And we do that by using a reversible exchange reaction at a metal center. So to do this in an NMR tube, we would have our solution containing our metal complex and the substrate, so the thing we want to hyperpolarize. We add parahydrogen enriched gas to the headspace of the NMR tube, and then we shake the tube to put the parahydrogen in solution. The parahydrogen adds reversibly to our metal center to form a pair of hydrides, and that metal center also binds one or more molecules of our target substrate. Now, if we carry out this reaction in an appropriate magnetic field, which is millitesla or lower, then we can observe a spontaneous transfer of spin order from our parahydrogen induced hydrides to the target substrates. Then, because everything's in reversible exchange, we can see an exchange between the bound and the free substrate. So we get hyperpolarized substrate free solution, and we see exchange of fresh parahydrogen onto the metal complex. So in this way, as we shake our tube, we build up hyperpolarization on our free substrate in a catalytic way, and then we can drop our NMR tube into our NMR detector to observe the enhanced NMR spectrum. So as has been remarked a number of times today, this is an extremely straightforward process to do in practice. So this is just my favorite video of one of the students, Olga Semenova, whose work I'm going to be presenting a lot of today, doing one of these experiments on a high field magnet. So she shakes the sample in the fringe field of the magnet, then drops the tube into the spectrometer and acquires the hyperpolarized results. So it's a very quick and straightforward process to carry out, although under the hood there's much more complicated chemistry and physics obviously going on. So I wanted to highlight how we carry out these experiments because it's very relevant to why we choose to couple the SABRE approach with our benchtop NMR detector. So if we're just thinking about the level of polarization we can achieve with the SABRE approach, we can think about the efficiency of transfer that is dependent on how much we've enriched our hydrogen gas in the para state and how much of the polarization potential associated with that is then transferred to our substrate. So in these experiments, what we've done is simple shake and drop experiments like in the video. So each point on these graphs is the average of several shake and drop experiments, where the hydrogen that we've used has been enriched to different levels of parahydrogen enrichment. So from all the way to near 25% at thermal equilibrium, up at room temperature, all the way up to near 100% at about 28 Kelvin. So by repeating these experiments for different levels of parahydrogen enrichment, and then observing the amount of polarization that we get on the substrate, on the target analyte for the different resonances, we can get a measure of the efficiency of the process. And we can see there's a nice linear correlation. And for a standard SABRE substrate like pyridine or methylpyridine, we're getting about a 6.5% efficiency for these orthoresonances that are closest to the binding site. Now we can improve efficiency by doing some selective deuteration, either of the substrate, which gives us about 16% under these experimental conditions, or both the substrate and the catalyst. So in this case, we've got our iridium catalyst, which binds 3 molecules of the substrate and the hydrides, and then has a stabilizing carbene here in the R1 position. And in the standard catalyst, we're using IMES as the stabilizing carbene, but in these more efficient measurements, this has been deuterated. And so we get over 20% efficiency. So SABRE has the potential to give very high percentages of polarization. But what's crucial about these results is that the buildup of the polarization happens outside of the detector. So it's in fact independent of the field that we use for detection. And so if we simply repeat these experiments, but instead of dropping the NMR sample into the high field magnet, we put it into our benchtop NMR spectrometer, then we find that we actually observe the same level of polarization and we have the same level of efficiency because the SABRE step is the same. And so what this means is for lower field devices where your thermal polarization is much lower, we actually see much, much higher enhancement factors than we see at high field. And so we get greater benefit of using SABRE on the benchtop and lower field instruments. And in fact, it's very common in the literature to see SABRE experiments done on benchtop type instruments. And you'll maybe remember that in Thomas's talk earlier today, the video he showed, they were detecting the nitrogen polarization on a benchtop instrument. So the question we wanted to ask as part of Olga's thesis was, can we use SABRE hyperpolarization to monitor reactions using benchtop NMR? So in order to test out this idea and to have a model system to look at, we decided to look at the reactivity associated with the SABRE catalyst itself. And so first I want to talk a little bit about what that reactivity is. So these measurements are all standard non-hyperpolarized high field NMR measurements to look at the reactivity, and then we'll look at how we can incorporate the SABRE process to follow it. So in a standard SABRE type experiment, we don't start with an active catalyst, we start with a pre-catalyst like this iridium species here. And when it's mixed with our substrate in solution, we typically have rapid conversion to our iridium-1 species here, where we've displaced the chlorine with a molecule of our substrate. So this is essentially our starting material, B here. Now, if we add hydrogen to our NMR tube and shake it to put it into solution, then we start the activation process and form this intermediate here, this iridium dihydride intermediate. And following further ligand exchange with an excess of the substrate, we eventually form the active catalyst species, which has 3 molecules of the substrate, parahydrides, and our stabilizing carbene. So in these high field NMR measurements, all we're looking at is the conversion from B to D over a period of time. So this is quite slow because we're not shaking or bubbling the parahydrogen. We just shake once at the beginning. But by looking at the resonances associated with the backbone of our carbene, we can clearly see conversion from B to D that goes to completion over several hundred minutes in the high field spectrometer. So this is our activation process that we would want to happen in order to do our SABRE experiments. And I should highlight here that our substrate is aminopyridine. Now, if we look at these experiments, these activation with aminopyridine, and we look, instead of looking at the carbene ligand, we look at actually the aminopyridine resonances, and we see something a little different. So there's something else going on here. So if we look at our aminopyridine, we have 2 proton resonances. We've got the orthoprotons highlighted here in blue that are adjacent to our binding site through the nitrogen. And we have the meta protons here highlighted in purple. And if we look at the meta resonances, we've got free aminopyridine in solution. We've got aminopyridine bound to our starting material, our starting complex, and we have aminopyridine bound to our product, our active species. And if we look at the time course of our reaction, we see consumption of starting material, consumption of some but not all of the aminopyridine in solution because we're working at an excess, and then we see formation of the product complex D. But if we look at the ortho position here, which is in blue, what we see is something a little different. We see consumption of the starting material, but we see far more consumption or loss of signal associated with that ortho position in the free material and the product material. And so what's going on here is that these experiments are being carried out in deuterated methanol. And the deuterated methanol is providing a source of deuterium, which leads to hydrogen isotope exchange on our aminopyridine. So on the same time scales our activation, we are getting incorporation of deuterium into the ortho position of our substrate. So this leads to the loss of ortho signal. So in the reaction monitoring experiments that I'm going to show you here using SABRE, what we're looking at is that the combination of the reactivity between the activation or the formation of the active catalyst and the incorporation of deuterium into the substrate. So it's well known in SABRE experiments that, and in fact in most hyperpolarization experiments, that you can't take for granted that the amount of signal you get, amount of hyperpolarized signal you get, is linearly or in a simple way dependent on concentration. So that poses a significant challenge if you're wanting to do reaction monitoring. So what we decided to look at here was not just the amount of SABRE signal we were getting as a function of time, but we wanted to look at changes in the hyperpolarized lifetime of that SABRE response as a function of time. And we can measure the lifetime in a single shot experiment quite simply. Here we're using a variable flip angle experiment, which basically divides up our available polarization into a fixed number of steps. And as the experiment proceeds, the flip angle use increases to account for the polarization that's already been sampled at previous points in the experiment. So how does this work, and why would we expect the relaxation lifetimes to tell us about these two different types of reactivity? Well, if you think about the active catalyst formation, what we have when we form the active catalyst is we have two different exchanging populations for our substrate. We have substrate bound to the catalyst and substrate in free solution. And we know that they have very different lifetimes. So in free solution, we would expect our substrate protons resonances to have much longer lifetimes than when bound to the catalyst. And so if we assume a rapid exchange limit, then what we would expect to see when we measure the lifetime of the hyperpolarization is a weighted average between these two lifetimes of bound and free that depends on the relative amount of the active catalyst and the relative amount of free substrate. So as we generate more active catalyst, we would expect our relaxation times, our hyperpolarization lifetimes, to get shorter. Now, if you think about the hydrogen isotope exchange, as we incorporate deuterium into our substrate, what we would expect for the meta resonances, so for the protons in the meta position, is that the proton that's adjacent to where a deuterium has been substituted, we would expect those lifetimes to get longer. Whereas any residual ortho protons, we would expect those lifetimes to be relatively unchanged by the progression of the hydrogen isotope exchange. So in order to attempt to probe these two different reaction processes, we're using a series of shake and drop experiments. So each point on these graphs is a single shake and drop measurement, like we saw in the video. And we're replacing the parahydrogen in the headspace of the NMR tube between each step. And so first, if we look at the results on top here, which is using detection at high field, when we're doing these high field measurements, we do a shake and drop hyperpolarized lifetime measurement, where we get a lifetime average lifetime for our ortho and our meta protons. And then we interleave that with a normal thermal measurement because we have enough signal at high field to see the progression of the reaction just using the thermal response for our meta proton. So what we can see from the thermal measurements is the activation, so the formation of the active complex, which is consuming free aminopyridine. But when we look at the hyperpolarized lifetime measurements, we see something interesting. We see two competing effects. So if you focus just on the ortho position here, so in blue, we see a reduction in the lifetime that corresponds to the activation process. But when we look at the meta, what we see is that there's a rapid increase at the beginning of the experiment in the hyperpolarization lifetime, followed by a decrease. And this increase comes from the incorporation of deuterium into the ortho position. So this is the hydrogen isotope exchange happening at the same time as our activation. So these two measurements that are happening at the same time then are telling us about these two processes. So this is all done at high field, and so we can repeat the same thing on our benchtop instrument, and we see the same effects where the ortho lifetimes show the activation, and in the meta lifetimes we see the combination of the deuteration of the substrate and the activation. Now, one of the benefits of using the benchtop NMR system is that we can easily work in protonated solvents, both because we don't have the problem with the lock, because we have an internal lock that's not based on deuterium, and also because the response is so much weaker from the protonated solvent that we don't need to do solvent suppression. And so if we rerun these experiments on our benchtop instrument in protonated methanol, where we've essentially removed the source of the deuterium, we see all evidence of the hydrogen isotope exchange reaction disappears, and we're left with just the evidence for the activation of the SABRE catalyst. So by this method and using the SABRE, we can see not only the effects of these two different types of reactivity on the benchtop instrument, but we can differentiate between them. And by using the protonated solvent, we can see the absence of the hydrogen isotope exchange. So these experiments, we're very pleased with these results, but there is an argument to say that by the fact that we're doing a series of shake and drop experiments where we're replacing the headspace of our NMR tube with fresh parahydrogen, where sometimes we're shaking and sometimes not, that we're actually interfering with the chemical processes. We're changing the chemical reaction conditions while we're doing the monitoring. So ideally, what we'd want to be able to do is to monitor this purely in situ, where we can maintain the same chemical conditions the entire time. So to attempt to do that, we are moving down into the ultra low field NMR regime. And in particular, we've chosen to do this using an earth field NMR detector. So this is a picture of just a commercial earth field NMR device developed by Meghan that's sold mostly just for teaching and for teaching basic MRI. And we've adapted it for use with parahydrogen hyperpolarization. So it's very simple. We just have a reaction chamber with a frit. We bubble parahydrogen through this chamber. It holds about a 4 milliliter sample. On the outside of our probe, we already have an electromagnet in the earth field device, and so we use that to generate our polarization transfer field. So if we look at our pulse sequence, we're bubbling parahydrogen continuously throughout. We switch on our polarization transfer field, so that allows the SABRE process to take place. We switch that off adiabatically and then detect the enhanced signal in the Earth's magnetic field. Now, because this sample is quite small and because the Earth field, even inside our NMR lab, is quite naturally homogeneous, we can get very narrow lines with less than a Hertz line width routinely, compared to with sort of a 500 milliliter bottle of water, where inside our lab we don't have such great field homogeneity. But unlike at high field, of course, we don't have any chemical shift information, so we just get a single resonance for these types of samples, such as pyridine. So because we have this in situ approach, we can actually look at the activation continuously. So we see a buildup of polarization as our sample activates and eventually reaches a steady state. And so each of these points is just a separate measurement. Now, we wanted to look at this reactivity not simply by the SABRE response, but we wanted to use the same type of relaxation measurement that I presented on the benchtop. Now, this is a bit more challenging on the Earth field because we're fighting for signal to noise. And in order to do a variable flip angle hyperpolarization measurement, we need to have very well calibrated RF pulses, which is a bit challenging, but we've managed to overcome that and get this working quite well. And if you compare the single shot measurements here with our pseudo 2D measurements, so much longer measurements where you do the T1 measurements step by step, we're getting good agreement across all our samples. So these are all pyridine with our catalyst, where we're increasing the amount of pyridine relative to the catalyst. And so you can see that's having a significant effect on the T1, where the more pyridine, so more free substrate there is relative to the catalyst, the longer the T1, because we're interacting less with the catalyst, and the catalyst acts as sort of a relaxation sink. So just finally, to show you some preliminary data doing the reaction monitoring with the single shot T1s, we can see that for this sample of pyridine, we are seeing evidence of a initial decrease in our T1 as the catalyst activates, and then it reaches a steady state once activation is complete. But these are, we're really fighting for signal to noise here. So these are relatively noisy measurements, as you can see from the error bars. And I should just say that this is in protonated solvent. And so we don't expect to see any effect of deuterium or hydrogen isotope exchange in these measurements. So we're hoping to further optimize these systems to be able to then go and look at deuterated solvents as well and see if we can see the same effects with the hydrogen isotope exchange in the Earth field. So that brings me to the end of what I wanted to tell you about today. So I just, a few sort of general conclusions. I would just say that SABRE is really an excellent hyperpolarization method for low field NMR. We can generate hyperpolarization quickly and renewably, and crucially, the polarization level you get is independent of the detection field strength you're using. And we've shown that using SABRE, we can follow some reactivity, particularly of the SABRE catalyst, and differentiate between deuteration and activation of the SABRE catalyst. And we're making good progress towards doing this in situ with earth field NMR detection under sort of continuous and controlled conditions. And lastly, just to acknowledge the members of my group, my collaborators who did this work. All the benchtop NMR work was done by a recent graduate of the group, Olga Semenova, and the earth field stuff has really been led by Fraser Hill Casey. And I'd just like to thank you for your attention.
Yeah, thank you so much for your talk. I will try to get most of these questions out, but if not, then we will have to resume this in Slack. First of all, a comment. You always said ultra low field for your earth field detection, but there are many ZULF people in the audience who like.
Sorry, I don't know if I'm frozen or you're frozen.
It seems like Soren froze up. Oh boy, do you want to take over?
I can ask one question.
Well, I can probably extrapolate from what I did hear of what the question is.
Okay, go ahead with that one first then.
So yeah, I mean the term zero and ultra low field NMR encompasses quite a lot of quite a range of things, and so what I would say we're doing here is sort of, we're still using a inductive detection, and we're still in the regime where the Zeeman term is the dominant term. We're not in the real zero field term. Once you regime, once you're getting down, I think most atomic magnetometers sort of kick their benefits kick in sort of 500 hertz or below or something like that. The earth field stuff we're doing is about 2000 hertz, but it's very much at the inflection point where, you know, the inductive detection coils are really struggling to give you much signal to noise, but you still are generally, most systems, your peak is coming from the Larmor frequency at the Zeeman, you know, from the Zeeman effect, not from the heteronuclear coupling.
Yes. Another question. So in the example provided, the substrate is shown to push out the chloride of the pre-catalyst prior to activation from bubbling with pH 2?
Yep.
Is this generally the case, and when do you see this happen versus a case where the substrate doesn't come on until either during or after activation?
So it's not generally the case in the sense that for some substrates, what you'll find, so if you make up your solution and then you walk downstairs and you put in your NMR spectrometer, so it's had some time to react. In the case of the aminopyridine, we would always see at high field complete conversion. You would only see B, as it were, in that scheme. So you'd only see complete, you know, you wouldn't see the chloride still bound. But for other systems, you might see, you know, some combination of chlorine bound and the substrate bound. And I know that there's examples where the active, it ends up, the chlorine ends up being part of the active complex. Like we have some systems where you're using coligands where the active species is actually neutral and the chlorine is still bound. So that complete conversion to B was very particular to this system.
Okay.